Okay. Hi, everybody online. Hi, everybody here in person. Thank you for coming. Thank you for being here. Yeah, as I was saying, I'm afraid it's going to be a little bit off from the workshop, but it's still combinatorics and homotopy theory. So I'm going to speak about the combinatorics of the permutahedron diagonals. That's a joint work with Bérénice Delcroix-Oger, Matthieu Josuat-Vergès, and Vincent Pilot in Paris, and Kurt Stockel in Melbourne. So it's a big team with very long names for this project, which is at the confluence of homotopy theory and combinatorics. So there's a really combinatorial part and there's some algebraic consequences. So the idea is to start with define what are permutahedron diagonals, then formulate some purely combinatorial results about these diagonals, and then deduce some algebraic consequences. So the starting point is to look at the actual set theoretic diagonal of a polytope, which is the map that you have on the screen, and to the basic observation that this map is not a cellular map. So, for instance, on the screen you can see the diagonal of the interval, which is in red, and it goes right through the square. So it is not a union of one-dimensional faces of the square. It's right in the middle of the two face. So what we're looking for is a cellular approximation to this diagonal. So for instance, we will be interested in deforming the red line into the blue line so that it is a union of faces in the product of the interval itself. This is a very, actually an old problem, and it's very important in algebraic topology because, well, it is essential to defining the cup product in singular and cubical cohomology. So the Alexander Whitney map, which you might know about, it is nothing else than a cellular approximation of the diagonal of the simplices. And Jean-Pierre Serre, when he writes his famous thesis, and he wants to use cubical homology, he needs to define, he wants to define the cup product, and for that he needs a cellular approximation of the diagonal of the cubes. And so here you have some pictures from Vincent. So he switched the colors over, but so in blue you have the set theoretic diagonal, and then in red you have the cellular approximation. So you can really see that, well, the diagonal goes right in the middle of the product of, in the first case, the triangle with itself, and the second case, the square with itself. But the cellular approximation is obtained by continuously deforming this central application. So cellular approximations for more combinatorially involved polytopes, this is much more recent. So it started with the work of Saneblidze and Umble in 2004, so for the associative and permutahedron. And here you have some pictorial representations of cellular diagonals for associative and permutahedron. I will explain in a second why these are actually representations. Yes, and the reason why I got interested in that is because it was part of my PhD thesis. So this problem of finding and describing a cellular approximation of the diagonal of the permutahedron was really instrumental in defining some higher algebraic structures. So first, how do you find such an approximation? There's a beautiful theory, which is called the theory of fiber polytopes, from Biara and Sturmfels in the 90s, who introduced the fiber polytope. So if you start with any projection, a fine projection of polytopes, there is another polytope which is associated to it, and which is made by averaging the projection over the fiber. So you do the Minkowski sum, Minkowski integral of all the pre-images of the fibers in the projection. And in this case, the one we're interested in here, it is associated to the projection that is really simple. You have P times P, and then you take 2 points, and then you do the middle point between them. So, for instance, for the interval, if you the fiber polytope, the diagonals polytope associated to it will also be an interval, and the vertices of this polytope are cellular approximation of the diagonal. So if you remember, we had like this diagonal in red, and then we wanted to deform it into an application that was cellular. So we had basically two choices. Either we deform it for going up, or we deform it going down. And these are the two, these correspond to the two vertices of the diagonal polytopes. And this, so such a vertex of the fiber polytope, it defines a section of the projection, which is the application that we're looking for. And selecting such a vertex, well, we can do it by selecting a vector that is in general position with respect to your polytope. So you take a vector in general position, it is maximized over the polytope at a unique vertex, and you can use it to define the section to the projection, which will be your cellular approximation of the diagonal. And the reason why I pictured the association in the permutahedron as I did is because when you have a section of this projection, well, you look at the image of this section, you project it down again, and what you get is a subdivision of your initial polytope. So maybe I should just go back to this image. Here, you look at the three-dimensional polytope, you send it into the product of itself with itself, so this is a six-dimensional thing, and then you deform the diagonal into something cellular, and then you project it back, and what you get is this subdivision. Okay, and this process, when you do it in the dual picture, you can see it as follows. So you take the normal fan of your polytope. So here, what is represented is the two copies of the normal fan of the hexagon. So we look at the hexagon. The normal fan of the hexagon is the braid arrangement, like these three lines that you see, for instance, the blue, green, the two blue and the green line. These are, this is the normal fan of the hexagon. And then what you do is you take this vector in general position with respect to your polytope, and you perturb your normal fan in this direction. And now you look at the intersection of the two normal fans. In this case, it's two families of hyperplanes, so you have an hyperplane arrangement. And this gives you this is exactly dual to the subdivision that is induced by the projection. So you can see on the picture, on the left, you have the two copies of the normal fan. And on the right, you have the subdivision of the hexagon that arises from a cellular approximation, a cellular diagonal. And so this actually appeared in algebraic geometry. So this is called the Fulton-Sturmfels formula. This is from a paper in 97, which is called Intersection Theory on Toric Varieties, where Fulton and Sturmfels, they define, so their goal is to define a cup product for toric varieties, but which are not necessarily smooth. So you look at what is called the operational Chow ring, and it's not at all clear how you should define the cup product, but what they do is because to every toric variety you have an associated polytope, and they look at the normal fan and they say, well, let's take a vector that is in general position, perturb the normal fan, and then look at the intersection. And I told you about the diagonals polytope. This is in their paper, actually. It's a little bit hidden, but it is there, and this paper appeared shortly after the fiber polytope paper. So these ideas are really the same. So this is where it comes from. So what we will be interested in is the study of the permutahedron. So permutahedron is this seminal object that appears everywhere because it encodes permutations, right? So what you do is you take the permutations of 1 to n, and you interpret them as actual coordinates in Rn, and then you take the convex hull of these points, and it so happens that you get a polytope which looks like the one. This is a 3-dimensional permutahedron, so it lives in R4, but it's in an hyperplane in R4, and so you can project it down quite easily to R3, and you get this picture. When you look at the dual, so the normal fan of the permutahedron is a hyperplane arrangement, and it's called the braid fan, or the braid arrangement. And when you take the pi1 of the complement of this hyperplane arrangement, you get the braid group. So here again, something that is really really central in many respects.
So
yes.
Can I ask a question? Is it saying in a sense that you can recover the braid group from the symmetric group? Or it's a very vague question, maybe.
Somehow, but you need to take the I think the Q completion of the pi1 of the complement of this arrangement. But they are very related.
Field framing group.
Yeah.
Yeah.
So, in summary, what I just told you is, well, to study the permutahedron diagonal, we just need to study generically translated copies of the braid arrangement. That's what we need to study. And these will encode iterated application of the diagonal. So here's the definition of the Ln braid arrangement. It's just family of generically translated copies of the braid arrangement. And so now we have, it turns out that these arrangements are quite interesting, and we can surprisingly obtain some closed formulas for their combinatorics. Basically, let's say now we're interested in counting the number of faces in these number of regions in these arrangements. So more precisely, we're interested in the flat poset of the braid arrangement. So it is the poset of intersections of the different hyperplanes that ordered by reverse inclusion. So here you have an example. So on the left, you have this perturbed braid arrangement that we're interested in, and on the right, you have the flat poset. And so to understand this flat poset and count the number of faces of each dimension in it, we'll find combinatorial objects. There are some combinatorial objects that encode this structure faithfully. And so, well, we look at partition forests. So what you take a tuple of set partitions of 1 to n, and you do the intersection hypergraph. So for each block in your partition, you make a vertex, and you link two vertices together if they share a common number. And well, the Ln partition forest, well, you take all these tuples of set partitions such that the intersection hypergraph is a hyperforest. Sometimes it might be all sorts of hypergraphs, but if you consider the ones that are hyperforests, you will actually obtain a faithful description of the flat pose set that we're interested in. And yeah, the pose set structure on these partition forests is component-wise refinement of partitions. So it's very simple structure. And to see that this encodes faithfully the flat pose set we're interested in, you just have to think about the definition of the braid arrangement. The braid arrangement, it's given by equating two coordinates with one another. So a set partition of 1 to n, it corresponds to a flat in this hyperplane arrangement. And then if you have, since you have generically translated copies, you will have that the flats of all these copies will be exactly the partition forest where the associated intersection hypergraph is acyclic. Because whenever you have something acyclic, you will have you don't have a well-defined intersection. And the refinement of flats, just at the level of the braid arrangement, it is given by refining of partitions, and so this also holds for the different copies. So now we have this. So on the top of this slide, we have an illustration of this flat pose set indexed by partition forests, and then we will, in order to count really the elements of this flat pose set, we'll need another bijection. So I didn't write the definitions in details, but here's just an illustration. So from the top to the bottom, you can go from partition forest to what we call rainbow forests, which are trees, labeled trees with some colors, and which encode, which are in bijection with the partition forests. And then once you have this translation, you can get quite directly some enumerative results. So for instance, if you want to count the vertices of your hyperplane arrangement, which correspond dually to facets of the diagonal, you have this very elegant formula. And the way you prove that you have this formula is to use what is called a prefer code to count these rainbow trees. This is a technique that is well known in combinatorics. If you want to enumerate trees, you can use a prefer code which encodes the construction of your tree. And so that's one of the results. You have the numbers at the end of the page. So for the little story, the second column. So first, when in my thesis I defined the cellular approximation of the diagonal for the permutahedron, I was in Montreal working with Hugh Thomas and explaining him, I found this thing. Like, here are my terms, and I was like, Guillaume, how many do you have? I was like, well, in dimension 1, I could say 1, 2, 8, and then I was counting in maybe 15, and I was like, okay, I didn't really know, but it was so natural to him to ask, like, how can you count this? How many are there? And then, so we made a little program, a computer program, and we went on the OEIS, and then it happened that it was a sequence of numbers that was known, and this was the first column. And now 2 years later, well, 3 years later, we have a complete description. We have the closed formula and the proof, right? So And this formula can even be refined by the same technique. So if you want to know not only the facets of your diagonal, but also, so all the facets of the diagonal, these are families of faces of the polytope. And you can fix the dimension of each of these components and ask how many faces in the diagonal have exactly these dimensions. And this is given by this very elegant closed formula, which took a very long time to figure out. But so yeah, if you just imagine for L equals 2, you have a diagonal of the permutahedron. You look at the facets, these are pairs of faces of the permutahedron, and then you can fix the dimension of 2 faces, and then you get this product formula for the number, for how many there are. And I should maybe emphasize that this result is true for any approximation of a diagonal. Here we didn't commit on making a specific choice. Any diagonal you're going to choose has this number of faces. So the other important thing that we are able to count is the number of regions of the arrangement, or dually the number of vertices of the diagonal. So if let's just state the result for L equals to 2. Vertices of the diagonal, these are pairs of vertices of the permutahedron, and they turn out to be, well, if you choose a direction that respects the Wick-Brewer order, these are intervals in the Wick-Brewer order. But these are not all the intervals, only some of them. But it turns out that when we can count them, and they are given by the number of such intervals. They are given by this exponential of Catalan numbers. But when you take different L's, you get Fus Catalan numbers. So this was quite surprising that such a closed formula could be obtained. Yeah.
What does this formula mean? What's Z?
Yeah. So Zn in brackets, it means the Zn coefficient in the series.
Okay.
So you take exponential of that, and then you take the coefficient of Z to the n, and then you get the number that you want. Yeah, so it's quite surprising that Fus Catalan shows up here. I don't really have an explanation. And also, yeah, you could already ask, because we counted the facets and then the vertices, but then is there some kind of interpolation? We had beautiful formulas for both of them, but it doesn't seem likely that we have anything that interpolates between these two. What we were able to obtain was, yeah, counting these two extremes, and then in between we get other things. So maybe just to give an idea of the proof, I mean, the fundamental idea is to use Zaslavsky's theorem. So Zaslavsky, it's a very classical theorem for arrangement of hyperplanes. It's one of the shortest PhD theses I've read in my life. He did this at MIT, and well, it's basically doing inclusion, exclusion. So you have an hyperplane arrangement, and you want to count the
skateboard. 今天下午论文答辩嘛，然后前期工作做了一些。
Okay. Yes, so you can count, when we say the f polynomial, it's just counting the f vector of the number of faces of each dimension, and you can do this in terms of the Mobius function of the flat Pope set. This is what Zaslavsky gives you, and well, you use again the description in terms of rainbow forests to determine the characteristic polynomial of the LN braid arrangement. And then once you have this, you can use, you can do some derivatives, which should be equal to 0, and then playing with the terms, you get the equalities that we want. So here's there's a little bit of dark magic somehow. It works, but it would be nice to have a bijective proof for this result, but we, as of now, we don't have one. So this was for the combinatorial part of the talk. So these are, so to summarize, you have this braid arrangement that you perturb in a generic direction, once, twice, 3 times, etc. And now you want to count the number of faces that there are in this hyperplane arrangement, and you can do it with beautiful closed formulas, at least for regions and vertices. Why were we interested in these combinatorics in the first place? It's because they have interesting algebraic meaning. So this construction, as well, you saw it was born in the hands of Fulton and Sturmfels, who wanted to define the coproduct for toric varieties. But it also plays a role in other parts, in algebraic topology, for instance. So here is maybe a little bit difficult to read slide, but it expresses a very simple idea, is the fact that the family of permutahedra, they are phase coherent in some sense, which is the following, that if you take a face of a permutahedron, it is isomorphic up to a permutation of coordinates to a product of lower dimensional permutahedron. So basically, faces of permutahedron, they are in bijection with set partitions, ordered set partitions, and then which each block in a set partition corresponds to a lower dimensional permutahedron. So here I've written the isomorphism. It looks a little bit complicated, but it's really not. It's just you take the shuffle permutation that puts back in order the coordinates so that this isomorphism works. So this is big theta, and we will need it in a second. So now I will call a diagonal of the permutahedron, of the permutahedra. So now we will be interested in a choice of diagonals for the whole family. So I choose in each dimension a diagonal for the permutahedra. And I will call such a choice operatic if for every face, and you can see a face, it is indexed by an ordered set partition, the map big theta induces an isomorphism between the product of the diagonals and the diagonal of the product. So basically, we want it to be, Saneblidze Umble called this property co-multiplicativity. Well, basically, you want the choice of diagonals to respect this structure, this coherent phase structure that has the permutation. And our theorem, which is quite unexpected, to me at least, is that there are actually only 2 such diagonals, which respect the Witt-Breuer order on the vertices. But if you don't ask for this, I mean, the permutahedron is really symmetric. So up to symmetries of the permutahedron, there's only 2. And so there's one, of course, that I studied, and there's a second one, and this is 10 pages of the paper, but I won't give more details about this here today. But we are able to recover the first construction of a diagonal by Saneblidze and Umble, and they did it by a very different method. So they did it purely combinatorially at the level of chains. So they didn't construct an actual topological map. And what we do is we say, well, you can if you choose the right vector, which I'm going to give you in the next slide, you recover exactly the diagonal. And yeah, the proof for that is some involved combinatorics that I'm happy to discuss about later. But I will hide under the rug. But let me give you at least, so I said that a diagonal was given by a choice of vector in general position with respect to your polytope. And let me give you the two vectors that give operatic diagonals. So first we look at the pairs of subsets of 1 to n that have the same cardinality and that have empty intersection. And now we're going to order these pairs by asking first that the minimum will be in the first term, and second that the maximum will be in the second term. So yeah, this is what they are. But we ask for this like in all dimensions. And the two operatic diagonals, they are given by vectors which satisfy the following formula. So you take the sum over I and big I of the VI's. This has to be strictly bigger than sum of the VJ's for, here's a typo, it should be J in big J. And either you choose the ordering with the min in I, or you choose the ordering with the max in J. And you can see that in both cases, the vectors will have strictly decreasing coordinates, because asking that if you take the size of I and J to be 1, then you will have that if I is less than J, then you have VI bigger than VJ. And this in both cases. So you can, and well, if you look at the braid arrangement and you take a vector that has strictly decreasing coordinates, it induces the Weak-Brugger order on the one skeleton of the permutahedron. So these are the two operatic diagonals. And then, well, how do you go on to prove such a result? You can do purely combinatorial proof. So you go inductively. So you start in dimension 0, and there's only one diagonal for the point. In dimension 1, if you choose to respect the Weak-Brugger order, there's only one choice. In dimension 2 also, the two choice of vectors that I gave you, they define the same diagonal. And this is something that happens. So you have different vectors that give the same diagonal. But when you arrive in dimension 3, then you have to make a choice. Either you take the LA or the SU diagonal. And the surprising thing is that once you've done that, if you ask for that the diagonals are operatic, this coherence, so basically what you're asking is that your choice of vector is stable under the theta map. So let's look just to give an idea. So you have choose one of these families of vectors, and then you look at the isomorphism theta, and like imagine that in the target you have one such vector, and then you pull it back along theta, you unshuffle it in this product on the left. And then you want each of the little segments to be, again, a vector in the same family. And so if you sit down with this problem, you'll see it's a purely combinatorial problem. It's not completely obvious. The proof is one page. But you can show that if you impose this condition, after dimension 3, there's no choice. You need to stick with one or the other, either the min or the max here, these choices. Okay, and so why is this result interesting? It's because it has implications for higher algebra. So let me introduce my favorite family of polytopes, the Operahedra. Well, these are polytopes that are associated with nested trees. So maybe some of you know about opertopes. So this is very baby case of an opertope. So you take a planar tree, and then you look at all possible nestings of this tree. So the way the picture I have in mind is you imagine that every vertex is an operation that takes number of inputs as a number of leaves and one output. And then, well, the nesting tells you in which order you perform composition of these operations. So in the picture, I compose first 1 and 2, then I compose the result with 3, then the result with 4, and then the result with 5. And what you get is a family of polytopes, which can be obtained by projection from the permutahedron. And well, these polytopes are really important because they generalize the associative and they encode the notion of homotopy opera. This is something that homotopy theorists care about. And so there's naturally there's an operad structure on this family of Operahedra, and now you can ask, if I choose a diagonal for each of these polytopes, I want them to be coherent with the operad structure. And the preceding result, it implies that there's actually only 2 choices. So for each polytope, you need to choose. You need to choose for all of them the same. If you want them to be organized into an operad structure, you need to make the same choice for all of them. And another reason why this family is such a family of diagonals is interesting is because it defines a universal tensor product of homotopy operads. I'm sorry if I'm saying big terms. Yeah, but this is a new object in algebra. It's something that it allows you to define a tensor product of these complicated algebraic structures by explicit formulas, and it turns out that there's exactly 2 operad structures. And this is because of what we did, so it's an easy corollary of what we've proved, because now if you have 2 planar trees, so you have a polytope associated to each planar tree. If you have 2 planar trees for which you make different choices, then I can find a bigger tree which has these 2 as subtrees. And the fact that I want coherence imposes that I have the same diagonal on each subtree of a given tree. So if I do different choices, I get a contradiction. So, but believe me, this proof is not it is not very difficult once everything else has been set up. But it is a very interesting result. It says that this is quite constrained of a problem, and there's basically 2 solutions to it. And there's an analogous result for another family of polytopes, which are important in homotopy theory, which are called the multiplyhedra. And this is exactly what we were talking about earlier. So the multiplyhedron, it's a polytope who's encoding morphisms between A-infinity algebras. So its faces are in bijection with trees with a gauge in the middle. So 2 colors, I see them as having 2 colors. And so here you have the 1-dimensional two-dimensional and three-dimensional multiplyhedra. And well, these were defined by Stashev in 1970, but they were realized as polytopes only in 2008 by Anfossi. So it took some time to realize them actually as polytopes and not only as Siebel complexes. But these are really important. I mean, they encode infinity morphisms between infinity algebras. These show up everywhere in the homotopy theory and also in other branches of mathematics. And the preceding results implies, based on some work that I did with Thibault Mazouire, is that there are exactly two operatic diagonals for the multiplyhedra and two operatic structures on them, and consequently exactly two tensor products of infinity algebras and infinity morphisms that are compatible with each other. So, and for instance, in symplectic topology, some people are interested in making computations, taking such a tensor product and making computations with it. And what we're saying here is you have two choices. If you want to work with something that is, well, if you want a formula that works for any pair of A infinity algebras and any pair of A infinity morphisms, you need to take the one that is given by either of these two diagonals. And the reason why this works, it's not completely apparent in the pictures, is that the multiplyhedra and the associahedra are both obtained as projections of the permutahedron. So once you set up the theory for the permutahedron via projection, you get the results for these other polytopes. Yeah, and I'm a bit early, but I guess I will stop here.
How can I think of are these two tensor products, they give like equivalent operands or? Yeah, that was my question.
Yeah, so from the point of view of homotopy theory, you can work with one or the other, whichever is most convenient for you.
Can you see this comparison at the level of the diagonal somehow, one way or another? Like, is there a diagonal level comparison that tells you that they will be the same later on?
What do you mean the same later? You mean homotopically?
So are you saying that they're homotopy equivalents, tensor products?
Yeah.
Is there a witness of that at the level of diagonals, whatever that means? Again, a very big question.
Okay. No, it's a good question. So at the level, first of all, at the level of diagonals, all diagonals are homotopic to one another because they're all homotopic to the cellular. There's always a way from going from one to the other, but in this case, we have a bit more. So if you look at the level of the permutahedron, there is a topological cellular isomorphism. And actually the isomorphism, this induces a topological cellular isomorphism of operads. So, and that's really non-trivial. I mean, the operad structure is really non-trivial. I hid it completely under the rug, but it's really non-trivial. And there's a topological isomorphism between these two. So it's very strong, strongly isomorphic. But at the level of permutahedron only so I don't want to commit for the operahedra and the multiplyhedra, but there's a possibility that it also descends there as well, so that they will be like as strongly isomorphic as possible. And at least for the permutahedron, there's a symmetry of the permutahedron that sends one diagonal to the other. And actually, there's many symmetries. There's more than one symmetries of the permutahedron that sends one diagonal to the other. So yeah, in this case, you have a very geometrical way of seeing it. I don't know if this isomorphism, though, is compatible with the structures, and I have some suspicion that it is not. I think it's asking a bit too much. So asking the isomorphism between the two operad structures to be, well, I don't know. It's something that I want to figure out, but yeah, does this answer your question? Yeah, feel free to ask. I feel like I gave some big words. If there's some definitions missing, of course. But of course, yeah, in the combinatoric seminar. But I wanted to emphasize these results that we have, because we have combinatorial geometric methods, and there are some consequences for higher algebra, at least for say someone that wants to work with these formulas for tensor products, and then you're like, which one should I use? Well, of course, they're all homotopy equivalent, but which one should I choose? Well, we're saying you don't have so many choices, and within these two, well, we also have very explicit descriptions of them.
Describe that. So in the beginning of your story, you were talking about the iterated diagonals. So in every level, this is still like so for binary diagonals, we have Saneblidze, and we have the Laplante-Anfossi plus 1, and that's the full set that works operatically. Does that hold in all iterations?
So what is it exactly that you're asking for? So you
so
want
you can,
them?
look at the diagonal that goes from permutahedron into the square of permutahedron.
Yeah.
Then in the beginning of your talk, you were given some numericals for the iterated diagonals that go from permutahedron to the bunch of permutahedrons. So for an iterated diagonal, it implied that there are also just two of them. One of them, for example, in the SA, SU, and another example in the LA.
I don't know. I would expect that if you want these morphisms to be morphisms of operads, then it must be the case. But the interesting thing about iterated diagonals is that, as you know, these diagonals are not co-associative.
Oh, yes.
So the different ways of iterating will give different formulas.
No, I meant the ones. Okay. So when you are writing the numericals, you are writing them for any.
Any.
Okay.
So we know that for any iteration, the number of faces will be fixed.
All right.
But then if you make a specific choice of diagonal, then the combinatorics will change. I mean, they should be isomorphic, but explicitly they would change.